Hi everyone, welcome to this walkthrough of LumenOps 360, which is a manufacturing operation intelligence project that I built from scratch. In the next few minutes, I'm going to take you through the entire journey from business problem that inspired this project through the data pipeline and the analytic layer, all the way to the business impact and the recommendation. Before we dive in a quick word, let's just talk about the structure of this project. I have followed the DMAIC cycle from Six Sigma, which stands for define, measure, analyze, improve, and control. That is the backbone of this entire project. Every slide you will see maps back to one of these five phases. So let us start with define phase, which is the why behind this project. So why did I build this project? Let me give you some background. I'm an electronics engineer by profession, and after my graduation, I used to work as a production engineer at LED lighting manufacturer in India. I was on the floor, production floor every day, and I experienced the operational bottlenecks, such as I saw lights flickering after assembly because of poor solder, poor PCB panel overheating, or any other technical reason. In addition, I saw housing getting damaged because operators were using the wrong screwing torque. Further, dust contamination on LED panel. And above all, operators were calling sick and nobody was tracking what that was costing us. Management was changing the production schedule in a mid-shift because the customer called with urgent order. Same defect, same firefighting, every single week, I lived that reality. Years later, when I was building my analytic portfolio, I came across Signify's 2024 annual report. If you are not aware of what Signify is, then it is formerly known as Philips Lighting. They are a 6.6 billion euro company, and their CEO disclosed the same very familiar problems. Order and delivery satisfaction had dipped. They had launched 200 million euro operational efficiency program. They had cut over 5,000 employees in 2 years. And all of this was happening while Netherlands had 97 job openings for every 100 unemployed people, which is tightest labor market in Europe. I recognized every single one of those problems. They were just described in boardroom language instead of the production floor language. So I thought, what if I model these exact problems at the plant scale? What if I build an analytical layer that I always wished I had on the factory floor? And that's how become LumenOps 360. So let's discuss the five root problems that this project is designed to address. The first problem is on-time delivery. It is at 80.6%, which means roughly 1 in 5 customer order is late. The target should be 95%. When I was working in manufacturing, this was the number one complaint. Customers were unhappy, the sales team is firefighting, and the production team is getting blamed, even though the root cause is often upstream in scheduling or material availability. The second is OEE, which stands for Overall Equipment Effectiveness. It is at 68.2%. Now, world class is, or the benchmark is considered at 85%. So we have a 17% gap here. But there is the thing that most people get wrong about OEE. They assume it is about machine breaking down. In this plant, it is not. It is about the changeovers and the rescheduling. That is a governance problem, not an equipment problem. So this is what the theory of constraint teaches us. Your output is limited by your bottleneck, and your bottleneck is might not be what you think it is. And the third is first pass yield at 96.7%. That might sound okay, but it means 3.3% of everything. It means 33 of 1,000 unit product has defect on the first inspection. And as we will see later in the SPC analysis, this process is not statistically stable. It is out of control. The fourth is staffing fill rate at 83.1%. This is Dutch labor shortage in action. The Netherlands has 97 opening for every 100 unemployed people. You simply cannot find enough operators. So shift routinely run below plant staffing, and nobody is quantify what that cost. And finally, overtime cost. 127,000 euros per year. That's the overtime cost. That is the band-aid. When you are short staff, you pay overtime to the compensate. But overtime is more expensive because per hour the workers are tired and their quality drops eventually. So it is vicious cycle. These five KPIs that we have discussed is the baseline for the entire project. In Six Sigma terms, this is the measure phase. So we now have numbers. The question is, what is driving them? Now we are in the tech stack of the project, but first let's talk about the importance point here, the sources of the data. First, it is MES, Manufacturing Execution System, which is a production floor system that captures everything happening on production in real time. Which SKU is running, start and stop time, operator logins, cycle time, downtimes, events with reason codes, and unit produced. The second source is ERP system, typically SAP in Netherlands. Signify runs also SAP. Our sales orders, material requisition, dispatch records, the customer data all lives here. When a customer places an order, SAP generates the sales order document. When a production floor needs material, SAP creates a material requisition. When goods ship, SAP logs the dispatch. Third is QMS, Quality Management System. This is where inspection result, defects and classification, disposition, decision gets recorded. The quality controller scans the batch barcode, record pass or fail, and selects the defect reason code from the dropdown. And fourth is SRM, or Supplier Relationship Management module, usually with SAP Material Management. The purchase order, goods receipt, supplier scorecard, lead time tracking, all of that sits here. Now in this portfolio project, I obviously do not have access to these real systems. So what I did was build a Python data generator that recreates realistic replica of what this system would produce. Those CSV files then loaded to the Duck database, which is a file-based analytical database. Think of it as SQLite or SQLite, for example, but designed for analytics. Zero infrastructure, no server to manage, just a single file. Then comes to transformation layer, which is built entirely in dbt. This is really important. I have a 27 dbt model organized in 3 layers: staging, intermediate, and marts. The staging layer takes the raw data and cleans it, rename the column, cast the types, and the intermediate level subsequently is where all the business logic lives. That is where OEE gets calculated, where first pass sale gets computed, where on-time delivery flags get set, and where the cost of poor quality gets rolled up. And the mart layer creates one model per Power BI page. So each dashboard page has single clean data source. One thing I wanted to emphasize here, that all the business logic lives in dbt, not in Power BI DAX. Power BI is for visualization only. This is a deliberate design decision. If someone wants to audit how OEE is calculated, they go to the dbt model, not to hidden DAX measure inside the Power BI file. I also have 61 dbt test, and it is the part of the map to control the phases of DMAIC that we just talked about, the process of Six Sigma. This tests enforce data quality at the pipeline level. Things like downtime reason must be from approved list, operator counts cannot exceed 1.5 times the plant staffing, batch IDs must be unique. If any of these tests fail, the pipeline stops. That is how you build the quality into the data itself. From there, the data feeds into two consumers, which is Power BI that connects to ODBC for 6-page dashboard, and the Jupyter notebook that connects to the same Duck database file for the statistical analysis, SPC control charts, and hypothesis testing. This is the executive overview, the first page of the dashboard. Think of this as the plant director's weekly pulse check. At the top, you see 6 KPI cards: OEE at 68.2%, performance at 82.55%, availability at 85.48, quality at 96.65, and cumulative on-time delivery is at 81.76%. And the staffing fill rate is 83.11%. Every single one of these is below target. That tells you immediately that this plant has systematical issue and not just a single point of failure. On the left hand, you have the OEE trend by month over the full 18 months period. Notice that dotted line is 85%, and that is the benchmark. Our OEE never even comes closer to the benchmark. It hovers around 68%. That is not trend problem though, it's just the level problem. The process is stable. It is just stably bad. We will confirm that with SPC later. On the top right, you see the top 5 customers by revenue. Exxon at 2.94 million, Gamma at 2.59 million, Praxis, Hornbach, Coolblue is followed. These are real Dutch retail companies that has OEM production with the company like LumenOps. I used a real customer name to make the project feel more authentic for Dutch hiring managers. Bottom left is the downtime by reason, and this is where it gets interesting. Changeover dominates 43,000 minutes. That is almost 30% of all downtime. And the second biggest is manpower short, so at 35,000 minutes. These two alone account for more than half of all the lost production time. This is Pareto principle in action, 80-20 rule. A small number of causes drive majority of losses. The bottom right shows on-time delivery trend by customer segment. You can see that the uh, retail consistently outperform B2B and the wholesale, which makes sense because retail orders tend to be more standardized. Page 2 digs into schedule adherence and on-time delivery. The business question here is simple. Where are we losing time in the order to cash flow? The KPI card shows OTD at 81%, late order value at 2.171 million euros, and average days late at minus 0.06. That negative average is a bit misleading because it means on average we are roughly on time. But that average hides a lot of variance. Some orders are very early and some are very late. The delay reason chart on the left side, it's Pareto analysis. Customer reschedule and logistic schedule are tied at 94 occurrence each, followed by packaging delay at 83, quality control holds at 81, and material shortage at 80, and production backlog at 79. What strikes me about this disruption is, or its distribution, is that it is relatively flat. There is no single dominant delay reason. That actually tells us something important. It tells us the problem is systematic. It is not one broken process. It is the whole system operating at suboptimal level. The delivery performance by product level on top right shows the 2 by 2 panel light. So there is a type of product called 2 by 2 panel light has the best OTD at 84%, while the most products cluster around 81 to 83%. Again, no massive outlier, just uniformly below target. The OTD rate by customer chart shows that Gamma and Action, the customers, at 83%, Honbach and Yumbo at 80%, Praxis and Carby at 79, all below 95% target. And the heat map at the bottom, as you can see on the screen, average days late by customer and month is where you can visually spot the patterns. The darker red cell shows period where specific customer were consistently delayed. If I were presenting this to a plant director, I would use this heat map to open the conversation about which customer relationships are at risk. Page 3 is probably the most analytical dense page in the entire dashboard. It covers OED decomposition, workforce impact, and bottleneck identification. Let me start with OEE. OEE we previously talked about that it stands for overall equipment effectiveness, and it comes from the total productive maintenance or TPM. At 68.2% OEA, 83.1% staffing fill rate, and 127,000 euros in total overtime cost, the story is clear. This plant is underperforming, and a big part of the reason is people, not machines. On the left hand, you see OEE by assembly line source. So we have two production lines, line A and line B. Line A at 0.69%, line A accounted for 0.69 and line B at 0.68 and line C at 0.67. These are very close together, which is interesting. It tells us that no single line is dramatically worse than others. Line B and line C are jointly the constraint. The following theory of constraint framework from Ali Goldrat, his principle is simple. The throughput of any system is limited by its bottleneck. In this plant, the bottleneck is not one line, it is two, which means improvement needs to happen on both simultaneously. OE by shift shows morning at 0.69 and evening at 0.67. That 2% point gap might not seem small. Might seem small here, but when you multiply it by production volume, it worth around 7,700 euros per month. We proved this statistically significant in the hypothesis testing notebook as well. Now, work for dimension on the right side, right? So the OEE versus staffing fill rate scatter plot is the chart that I'm the most proud of this entire project. Each dot represents a shift. You can clearly see that the staffing drops, OEE drops with it. The bottom right chart, OEE by staffing level, quantifies this. Fully staffed shifts achieved 0.71 OEE. Severe shortage shifts dropped 0.65. That is a 6% point gap. The overtime cost trend in the middle right shows the cost of composition for understaffing. It spikes around September to November 2023. This is the Dutch labor shortage made visible in plant data. In OECD's 2025 economic survey of Netherlands, they wrote that persistent labor shortage weighed on the potential growth. This page is what the statement looks like at the plant level. Page number 4 is the quality page. This is where we enter the heart of the Six Sigma analysis phase. The first pass yield at 97.60%, cost of poor quality, which is COPQ, at 979.72 thousand euros. The total rejections at 62,000 units. These are the headline numbers. The defect Pareto on the left shows the top defect types ranked by frequency. Poor packaging leads at 11,000 rejection, followed by housing scratch, dust contamination, housing damage assembly, and flicker at 7,000. Every single one of these defect codes comes from the real experience. The defect heat map at the bottom left, reason by product category, shows the interaction between defect type and whether the product is indoor, industrial, or outdoor. Housing scratch is worst in indoor, which makes sense because indoor fixtures have more visible surface. The first pass yield 10 on top right shows monthly variation. Notice it hovers right around 97% target line. Some months are above, some months are below. This is where SPC becomes critical because it just look at the trend line, does not tell you whether the variance is normal or whether the process is out of control. So we'll see it in the next section, that is SPC, reveals the process is not stable. The rejections by quality control stage donut chart shows that the 70.45% rejection happens at the production quality control and 29.55% rejection at packaging level. This is useful for root cause analysis because it tells us that most quality problem originate during the assembly line and not during the packaging. So that is where correctiveness action should focus. I also created a separate fishbone diagram, also known as Ishikawa diagram, for housing damage. It covers all 6M, like man, machine, method, material, measurement, and environment. That document is inside the docs folder of GitHub repo. Page 5 focuses on material and supply risk. This page directly mirrors one of the biggest concerns that Signify's CEO discussed publicly. He acknowledged that the component shortage pushed 3% of quarterly sales into next quarter. That is massive number for 6.6 billion euro company. LumenTech BV, which is our portfolio project company, has 4 suppliers. 2 are in China, 1 in Germany, and 1 in Taiwan. 2 of the Chinese suppliers, as the names are Guangdong Optochip and Shenzhen Circuit Pro, are single source supplier. That means if either one of them has disruption, whether from tariff, logistics, or quality issue, there is no backup. That is critical vulnerability. The supplier reliability scorecard in the center is the key table. It shows each supplier component type, country, whether they are single source, their on-time delivery rate, average lead time variance, and defective quantities. Shenzhen Circuit Pro has the worst profile, single source, 85% OTD, positive lead time variance, meaning they tend to be late, and 3,429 defective units. The supplier on time delivery, OTD, trend at the bottom left shows the monthly performance over 18 months. You can see significant volatility with some supplier dropping below 70% on time delivery in certain months. The tariff exposure chart on the top right, as you can see, it reveals the financial impact if tariff were to double on Chinese import. Given the geopolitical environment in 2024 and 2025, this is the most hypothetical scenario. This kind of scenario modeling is exactly what supply chain teams at companies like Signify are doing right now. The material shortage incidents chart on the bottom right shows a clear spike around mid-2023, which correlates with the period when global component shortage were still unwinding. In the lean terms, this page addresses inventory waste, which is one of the 8 wastes in the Team Woods framework. Holding excess material to buffer against supplier unreliability is waste, but running out of material and stopping the production line is even worse. On this page is strategic scenario page, and this maps to the improvement phase of DMAIC process of Six Sigma. This is where we stop describing problems and start quantifying solutions. PKPA card at the top, schedule fees saving at 21,000 euros, staffing improvement saving at 3 million euros. That is the annualized figure if we could get to the full staffing. And the total changeover cost which is 107,000 euros. The changeover cost by line chart shows that all three lines have similar changeovers cost, roughly 34 to 36,000 euros each. This makes sense because all three lines runs at the same SKU mix. The average daily changeover trend shows fluctuation between 0.25 and 0.35 changeover per days. Now, this might seem low, but remember, each changeover event costs OEE. Our hypothesis testing showed that shifts with changeover lose 8.56% point of OEE compared to shift without one. That is the large effect with correlation of R equals to 0.571. The scenario impact by line table on the right quantifies three improvement scenarios for each line. Scenario 1 or scenario A, which is a scheduled freeze. Scenario B, which is staffing improvement and associated changeover cost over time, associated change over cost or overtime cost. Line 2 shows the highest scenario, A saving at 7.3 thousand euros. Now the downtime distribution donut chart confirms what we saw on page 1. Changeover at 29.62% and manpower shortage at 24.35% are the top two costs. Together they accounted for over a half of all downtime. The beauty of this page is that it speaks the language of operations directors. It is not saying your OEE is low. It is saying if you improve or if you implement 48 hours schedule freeze policy, you will save 21,000 euros per month in changeover related to the losses. That is actionable, and that is the kind of insight that gets budget approved. This connects to the asset-light manufacturing trend Signify is pursuing. They are consolidating from 41 plants globally. If you were advised on which lines or which production lines to consolidate, this is exactly the kind of analysis you would need. Now we are at the statistical evidence. This is what separates this project from typical dashboard portfolio. The dashboard shows you what is happening. Statistics tells you whether it is real. On the top left is the P chart for daily defect rate. This is the statistical process control chart invented by Walter Skewhart in 1920s. The chart line shows the average defect, which is at 2.13%. So that's the average defect rate. The red dashed line are upper and lower control limits calculated at plus and minus 3 standard deviation of the average defect rate. Any point outside those limits is out of control. You can see the red dots scattered throughout. There are 73 out of control days out of 18 months. And when I applied the Western electrical rule, which applies a set of additional patterns that signal the instability, 49.4% of days skewed that showed at least one violation. The process capability index, which is CPK, is only 0.669, which means the process is operating at about 2 sigma. For reference, 6 sigma aims for CPK of 2.0 and above. We are nowhere near to that. What does this mean practically? It means this plant needs process stabilization before it needs to process improvement. You cannot improve a process that is not stabilized. So you first need to find and eliminate the special cause of variation. Then once the process is stable, then you can work on shifting the levels. On the bottom left is the hypothesis testing for changeover effect. This is the most single important finding in the entire project. I tested with the shifts with the changeover event. Remember changeover means that suddenly any customer came with any urgent requirement and the entire change in the production plan. So this is recalled about the changeover in shifts. A statistically significant lower OEE than shifts without one. The answer is an empathetic yes. This p-value is less than 0.001. The effect size using rank Biserial correlation is R equals to 0.571, which is classified as large effect. In practical terms, changeover shift lose 8.56 OEE%. That translates to 42.348 thousand euros per month in lost output capacity. On the right panel, you can see the summary of all hypotheses. Every single one of them was rejected at alpha equals to 0.05. The changeover effect is largest by far, followed by understaffing, and then line level differences and evening shift differences. So here's the bottom line. Everything we have analyzed, the dashboard, the SPC charts, the hypothesis test, it all comes down to this point. Roughly 798,000 euros per year in addressable improvement opportunity. Let me break that down into 3 actionable recommendations. Number 1, scheduled freeze. So what exactly is scheduled freeze? We just recently talked about as well. So this is the biggest lever. If we implement a 48-hour of scheduled freeze policy, meaning no change into production plan within 48 hours of execution, we can significantly reduce changeover frequency. Our data showed that shifts with changeover lose 8.56 OEE percent point. The effect size is R equal, which is R equals 0.571, which is classified as large. That translates to 42,348 euros per month in recovered capacity. This is not about buying new equipment. We don't need to really invest anything here. It's just the policy that we need to change. It costs nothing to implement. Number 2 is staffing optimization. If we improve the staffing fill rate from the current 85% to 95%, we can recover 3.33 OEE percent. That is 16,490 euro per month. In the Dutch labor market, where there are 97 vacancies per 100 employed, this is not easy, but it could be addressable through a combination of temporary agency works, shift premium incentives, and cross-training existing operators to cover multiple positions. And number 3 could be shift standardization. Our data showed that evening shifts underperform morning shift by 1.55 OE point. So that is worth around 7,695 euros per month. The fix here, the process standardization, ensures that the evening shift supervisors follow the same startup and handover protocols as the morning shift. The combined these 3 levers recovers about 13.4% point of OEE. At current production volume and the margin, that is roughly around 66,500 euros per month. So annually, this amount could reach up to 798,000 euros per year. And so let's wrap up. This project represents the full cycle of manufacturing analytics. We started with the real problems from the real factory production floor. We modeled them at plant scale using a fictional Dutch company. We built a reproducible data pipeline from Python through DuckDB and dbt. We created a 6-page Power BI dashboard that covers every single or every major operational dimension like schedule adherence, OEE, quality, supply risk, and strategic scenarios. We backed every finding with statistical evidence, SPC control charts, and 5 formal hypothesis states. And we quantified the total improvement opportunity is roughly around 798,000 euros per year. But I wanted to end on this one thought that the reason this project is that the project works, it's not the technology, it's not the tools, but what makes this project different is the defect code like flicker or housing damage assembly, dust contamination, or they're not from textbook or any reports. They are from the real work experience. I have held this product in my hands, and that real experience is what makes analysis credible. If you're interested in the full details, the GitHub repository has everything. The DBT models, the notebooks, the framework documentation, and the live Power BI dashboard as well. So thank you for watching. If you have any questions or feedback, please leave a comment below.